All right. Welcome to this workshop on geospatial machine learning, where our goal is going to be to take some building fires in San Francisco and try to predict the risk of those fires throughout the city, despite the fact that some of those areas haven't actually experienced a fire in recent years. My name is Ken Stife. I am the director of the Masters of Urban Spatial Analytics program at the University of Pennsylvania. I'm also the founder of Urban Spatial, a similarly named consultancy at the intersection of data science and public policy. And in both those capacities, I am interested in converting data into something actionable that a government can use to make someone's life better. And much of the work we do is spatial in nature, and this is going to be one use case of that. I'm going to jump into it. As you may be able to notice, I am in R Studio. This entire workshop is going to be in R, and it's a lighter and more simplistic topic than what's covered, a similar topic that's covered in my new book called Public Policy Analytics, Code and Context for Data Science and Government. It's being published in August of 2021 by CRC Press. It is also available as open source online. You can Google for it. I hope you'll check it out. It provides a whole number of use cases, including machine learning use cases for doing data science in government. All right. As I mentioned, this this video is an abridged version of chapter 5 in the book, which is on predictive policing. By predicting fire risk, we get to avoid some of the biasing pitfalls of predictive policing and focus more on the mechanics of doing the analysis. In the end, we're going to wind up with a measure of fire risk for every location in San Francisco. And our hypothesis is going to be that fire risk is a function of exposure. Exposure from a location to nearby risk or protective factors. So for instance, the closer we are to some kind of blight, we might posit the higher the probability of fire risk. And you're going to see we're going to come up with a whole host of risk factors. We're going to measure exposure to those risk factors. We're going to put them in a regression model, and the prediction from that regression model effectively will be some measure of risk for every location in San Francisco. Now, for those of you with some GIS, Geographic Information System, or spatial analysis experience, you're probably pretty familiar with a map like this. This is a hotspot map or a kernel density map of building fires in San Francisco. You can see this big hotspot in the Northeast. This is in the Tenderloin neighborhood. And this is the traditional way that we view risk. Specifically, we look at the points on a map, we generate a hotspot map from those points, and the intelligence is revisit the past locations of adverse events, which is to say, if you're a fire department and you want to understand risk, go where fires have happened in the past. This is the traditional way of doing it, and I want to suggest to you that this is a departure from what I hope is the innovation that I'm going to show you today, where it's not just about revisiting past locations. What we want to try to do by understanding the underlying spatial system, by understanding the exposure to certain risk factors, that we can predict fire risk, even if a fire hasn't occurred there before. So it may be reasonable to go and look for fires where fires have occurred, but it may also be reasonable to look for fires where they're at risk for occurring but haven't actually occurred. And what I mentioned in this workshop is that by understanding the underlying spatial system, we can understand why things occur, where they do, and that'll give us a better predictive understanding, which is important if we're going to actually allocate some resources, if we're a fire department. So fire is a relatively rare event, and in this kind of analysis, what I suggest the goal is to understand the latent risk for fire, which is to say that the risk for fire is much greater than the number of fires that actually observed. So what we're going to do today is to predict that latent risk. And the key consideration in pretty much all the models that I build in this book is that our model is generalizable to different communities, despite the fact that those communities vary across factors like race or class. We want our predictions to reflect fire risk and not any of these other potential biasing factors. And so one of the ways we're going to try to get at this idea of generalizability is through the process of spatial cross-validation, which will be new to you if you are new to machine learning. Cross-validation will be old hat if you are familiar with machine learning. Perhaps the spatial variety will be new for you as well. So I just want to give you a sense for what we're going to be working towards using this map right here. Beginning on the right, here you can see we've partitioned the city of San Francisco into these discrete grid cells that we call the fishnet. And here you're looking at the count of fires for every grid cell. Moving over to this middle map, this is the hotspot or kernel density. This is if we conceptualize risk as the locations where fires have occurred in the past. And finally, we're going to have these risk predictions from our model. Places that we believe are at risk for fires based on this idea that they're exposed to these underlying risk or protective factors. And what we're going to do is draw a distinction between these two, between the risk predictions and the kernel density. We're actually going to assume that the business as usual way that, say, a fire department understands risk is with this kernel density. And we're going to ask if our risk predictions are, quote unquote, a better tool for doing something like fire inspection relative to this kernel density, but more on that in a moment. So very quickly, here is the agenda. The next section is going to be wrangling the data we will need, the fire data, as well as the features we will use to predict fire. Section 3 is we're going to try to understand the spatial process of fires, which is to say, can we engineer predictive features that will account for the underlying spatial pattern of those fires. In section 4, we will build a model focused on spatial cross-validation. And finally, section 5, as I mentioned, we're going to compare the risk predictions to the kernel density. Which algorithm is best suited for doing some sort of resource allocation like fire inspection? At this point, let me mention that this entire RMD is available on a GitHub repo that you can see in the description for this video. In section 2, we'll begin by loading a series of libraries. I do want to mention a couple of these that you may be unfamiliar with if you're new to spatial analysis. The SF, or Simple Features library, is a must-have for doing spatial analysis in R. R-Socrata is a package for downloading open data, which we're going to rely on exclusively for this analysis. And some of these other functions that some of these other libraries that you see here will help us do the analysis, and I'll go through them when we actually see them. And finally, here is a list of functions that come with the book. These, we're going to use 2 of these functions. You'll see them momentarily. So let's begin with the fire data. And we need to define some sort of spatial extent, which is San Francisco. So we're going to read in a whole bunch of neighborhoods directly from the San Francisco Open Data site. If you're unfamiliar with the San Francisco Open Data site, please go Google it. It is an incredible wealth of free data, much of which is spatial in nature. Many cities have these open data websites. I urge you to Google your city and the term open data. So we'll download neighborhoods. We will download a boundary for the city of San Francisco. We'll download some streets from which we'll generate some main streets that will help our base map. And finally, we will develop a unit of analysis, which we call the fishnet, which, as you'll see momentarily, is a lattice set of grid cells. Here you can see they are at a 500 by 500 foot resolution. How do I know they're at a 500 by 500 foot resolution? Because the data that I'm downloading, I am projecting to be in a coordinate system of feet using this ST transform. And this is what the outcome looks like. So we have San Francisco. And what we've done is to build this 500 by 500 grid cell unit for every location in San Francisco. If you're a GIS nerd, this may look like what we call a raster map. These grid cells are actually polygons. They are vector polygons. And you'll see why this is important. We need to partition San Francisco into these discrete spatial units so we can, in the end, have a measure of fire risk for every location citywide. All right, moving on. Now we're going to download the fires. And there is an open data website for the fires. We're going to use the function called read Socrata from the R Socrata package. It points to the fire incidents data set. And I'm using just a quick query to only pull down the building fires, what they call primary situation. And those are 111 building fires. And from this, I'm going to mutate from the incident date a year. I'm going to return only fires from 2017 and later. I'm going to make sure I encode them as points as a particular type of simple features, which is the library of spatial analysis that we're going to use for this analysis. I am setting their coordinate system to be in geographic coordinates, but then transforming them into the same coordinate system as our neighborhoods, which is in feet. And finally, I'm doing a spatial subset. That's this last line, a spatial selection to return only those fires in our study area. And here you can see our fires. Once again, you will notice that if you kind of blur your eyes, a hotspot of these points in the Tenderloin region in the Northeast. But you can see there are fires spread throughout the entire city of San Francisco. Now, what we're going to do is to train our model on fires from 2017 through 2020. And we're going to set aside in this line of code here, fires from the year 2021. And we're going to use that to test our model. This is a very common approach if you're used to machine learning. Obviously, it's unimpressive to train our model on some fires from some years and then test our model on those same fires. That doesn't tell us if we've created anything interesting or important. It just tells us we can predict for the data the model has already seen. So we're going to set aside a set of fires just from 2021, and we'll stick to this layer fires 17 through 20 for doing the majority of our analysis. Now, I mentioned to you that the general way with which we look at fire risk or risk of adverse events is to look at this kernel density. We saw this map up above. I just want to show you how we create it. It's using the SPAT-STAT package. And the first thing we do is to convert our fires to a PPP layer, which is unique to SPAT-STAT. And then we create this kernel density. And we're actually going to, in this line of code, we're going to convert it back to a R data frame and then to an SF. And we're actually going to spatial join it to our fishnet, to our grid cells, using this aggregate function. So the input is going to be our kernel density. We're going to spatial join that to the fishnet, and we're going to take the mean density for every grid cell. Once I use ggplot to plot it, it looks like the map we have above. And again, we can see this hotspot in Tenderloin. All right, the next thing we need to do is to get the fires into a layer that I'm calling FireNet. And what that will give us is a count of fires for every grid cell. And the way we create this is by taking our fires from 2017 through 2020, giving it a variable called count fires equal to 1, and then again, spatial joining it to our fishnet using the aggregate function and taking the sum. And you can see here we have the count of fires for every location in the fishnet throughout San Francisco. All right, now that we have fires into our fishnet, we have to get our risk factors, our independent variables, into the fishnet as well. And we're going to start with a series of factors related to land use in San Francisco. There is a very amazing open data set called land use. And here I'm pulling in the GeoJSON directly into R using the stread function. I'm just removing some of these are building parcels, by the way. There is, if your house, if you have a single family house, that's on one parcel. Maybe you live in a multifamily apartment building. That apartment building is on a single parcel. So I'm trying to find parcels that actually have some building square footage, and those that are built between 2021 and 1901. And again, I'm projecting that into the same projection as neighborhoods, so we're dealing with feet. Now, the first thing I'm going to do is to hypothesize that fire risk is a function of exposure to vacant parcels. I have a really good sense that distance to blight, that places that are really close to blighted parcels may be at risk for fire. Maybe those are places that don't see a lot of attention. They're older, they're falling down. Maybe there are hazardous chemicals there. There's a whole reason to believe that exposure to vacant parcels is a good predictor of fires. So in this code block here, I am pulling out, I have to actually download the land use parcels first. This is a bigger file, so it might take some time to download from the open data site. I am going to create a layer called vacant, where from the land use file, I'm pulling out just those parcels that have land use equal vacant. And then in this third line here, I'm converting them from parcel polygons to parcel centroids. If you're unfamiliar with the centroid, try to imagine a pizza box. And if you were to put your finger under that pizza box to balance the pizza box, that's the centroid. It's the gravitational center. It's very easy to understand or conceptualize a centroid for a pizza box because it's perfectly square. Same thing for a plate. It's interesting. Centroids can take on all sorts of strange spatial relationships if you think about parcels that are not as linear as a square or a circle. But it's the gravitational center. So we've moved from polygons to points. It is still reading in those land use parcels. Once I have my vacant building centroids, I'm going to create a new layer here on line 224 called varsnet. That varsnet will hold all of our independent variables. The way it is going to work here is that I'm going to, again, spatial join using the aggregate function, the number of vacant buildings in each grid cell. And in the end, let's see what happens if I check out varsnet. You can see it's a layer. It is a polygon layer. And most of the grid cells have 0 vacants in them. There are 5,394 features or grid cells. And here you can see the geometry for each. So it's simply a simple feature data frame. But in this varsnet, we now have a measure of the count of vacants. And let's visualize this. Here we have a map of those vacant counts. And I want to ask you, what do you make of this measure of exposure? I'm not a big fan of this measure of exposure. Yes, we can see some grid cells that have counts of vacant. But if you look at one of these black grid cells that are close to or adjacent to a grid cell that has a vacant, think about how we conceptualize of geographic exposure. It says that this is a value of 0 right here, but in reality, 500 feet away is an actual vacant. And this just seems a little bit too abrupt for me. I want to think about a way of conceptualizing this geographic exposure for every location in San Francisco, and not just the ones that actually have vacants inside of them. And the way we do this is with a measure called average nearest neighbor distance. And this is actually an example from the book. Here in the book, we're thinking of houses and assault crimes. And you can see in the image on the left, the house is in orange, the assault crimes are in green. And what we've done is measure the distance from its house to its four nearest assault crime neighbors. You can imagine taking the average of those and compare that average to that on the right, where the assault neighbors are clearly farther away. In general, the map on the right has a higher average nearest neighbor distance. So it is perhaps less exposed, the map on the right, the house on the right is less exposed to assaults than the house on the left. And in order to calculate this average nearest neighbor distance, we're going to use a function that I provided for you called nearest neighbor function. Just to make this code block a little less verbose, I have converted the ST coordinates and ST centroid functions that come with the simple features package to STC and STcoid. And you can see I'm going to create a new feature in my varsnet layer using the mutate command. That feature is going to be called vacants.nearestNeighbor.nn. I'm going to use the nearest neighbor function to measure the nearest neighbor distance from every grid cell to its 3 nearest vacant neighbors. And it's a pretty fast function. And in the end, I get a data frame as we saw previously, but I have this new row, average nearest neighbor distance to vacants. And we can look at the outcome of these two measures of exposure. We saw the map on the left already, where we're just looking at count of vacant for every grid cell. But the map on the right has this surface of exposure, because there's a measure for every location in San Francisco, its relative exposure to vacant properties. My preference is this map on the right, because again, there's a measure of exposure citywide. All right, the next thing we're going to do is to develop 2 more important features for our model. The first is we're going to take the mean year built, a measure of how old a property is. We might hypothesize that older properties are at higher risk of fires. And we'll also look at the average square footage of buildings in that neighborhood. And we're adding those to the varsnet. Let's map one of those. Here is a map of mean year for parcels built. I really like this map because it shows that different areas of San Francisco were developed at different times. For the GIS nerds among us, you can see that the age of a property in San Francisco is highly clustered or spatially autocorrelated, and even on a neighborhood level, which I think is particularly interesting. So you can imagine now, we keep adding to our varsnet layer more of these features. The next thing I'm going to do is we're going to add some graffiti data, exposure to graffiti. Our hypothesis, again, about blight, we might say that places that have a lot of graffiti are at high risk of prediction. There is a graffiti 311 open data page. 311 is a system by which residents call to report some kind of minor quality of life infraction like graffiti. And the hope is that the city will come and clean up that graffiti. Now in San Francisco, there are hundreds of thousands, if not more, instances of graffiti citywide. So I'm using the limits tag in the read Socrata function, basically to download a 5,000 incident random sample. I project them. I am subsetting for only the study area we have. Let's download those 5,000 random points and we'll map them. There they are. There is graffiti all around San Francisco. Again, my eye is drawn to the fact that there's many of those points in and around our location of interest, where there's that giant fire hotspot in the Tenderloin. Again, I'm going to, instead of just looking at count of graffiti features, I'm going to use our nearest neighbor function to calculate the average nearest neighbor distance, in this case to 5 graffiti reports. And that's what this map shows. Again, we get a measure of graffiti exposure for every location in the city. And now we have a small set, good enough for demonstration purposes, small set of risk factors. We know the count of fires for every location, and we're going to create a new layer called final net, where we're going to put together our fire net with our fires as well as our VARS net. And the last thing we're going to do with final net, just so you know I'm not lying about it, here's our final net. You can see it has count fires. It has our vacant nearest neighbors, year built, building square footage, and graffiti exposure. And the last thing I'm going to do is I want to know which neighborhood every location is in San Francisco. So I'm going to use the stJoin function to do another spatial join and spatial join the neighborhoods to the final net. And this map's going to look a little bit funky because of the blocky nature of our fishnet. Here it is. So every grid cell now knows what neighborhood's in, which is going to be really important when we start doing spatial cross-validation. We're going to hold out individual neighborhoods. All right. The next section is all about trying to understand the spatial process of fires in San Francisco. And specifically, we're going to try to engineer some features that might use the underlying pattern of fires to help predict fire risk, and specifically fire hotspots and cold spots. So we're going to use a linear regression model. And if you have any experience with linear regression, you know it's often difficult to predict the outlying high and outlying low areas. But that's really important for us, because if we underpredict the hotspots, what we're doing is under predicting areas that are otherwise high risk. So we want to try to factor in some of the hot spots and cold spots into our analysis. And we're going to do that using a pretty classic spatial statistic called the local Moran's eye. It's a null hypothesis test. And the idea is that every area is going to look at very adjacent areas and ask, is fire in my location clustered relative to my neighbors? Is it effectively a hotspot? And typically this kind of analysis, trying to understand statistically significant hotspots, is really important for doing exploratory spatial analysis. But we're going to take it one step further by actually engineering features into our model. The first thing we do when we create this local Moran's eye is to create what's called a spatial weights matrix. This is another example from the book in the city of Chicago. Here we're going to relate that one black grid cell in the middle to its very adjacent neighborhoods, all of the grid cells that touch it. And we're going to, again, ask the extent to which the fire counts are clustered in this area. To create the spatial weights matrix in R, we actually have to first convert our fires, our final net, which include our fire count, into a different form of spatial data. And then we can create the spatial weights. I provide a great deal more context about what's going on here in this entire section in the book in chapter 5, and I urge you to check it out. I'm really going to go through it very quickly, these lines of code, because they're a little verbose. And in fact, since I've written the book, there's a package that has come out. I'm sorry, I'm forgetting the name. That would actually make this whole process a lot less verbose. It makes this a lot more tidy. But this is what we have for now. What I'm going to do is I'm going to measure using this function local moraine on the count of fires from my fire net using my spatial weights matrix. And I'm going to engineer 3 fields out of that. The first is called fire count, which is simply the count of fires. The second is the local Moran's I. And the third is the p-value or statistical significance of that measure. And then what's interesting about that statistical significance is that I can create a variable called significant hotspots. So if the clustering is very significant, which is to say that it's smaller than our magic threshold of 0.05, then I can flag it as a significant hotspot. And the bottom part of this code block uses a for loop to create the map you're going to see with 4 different legends. So the first thing we see in this map is fire count on the left. We've looked at that map multiple times. The next map here is the local Moran's I measure, which you can see is particularly pronounced again in the Tenderloin area in the Northeast. But I'm really interested in this p-value measure because again, there's a measure for the entire city. And those areas that are really dark close to black are those places that are highly significant local clustering. And there on the bottom right, you can see the significant hotspots. These are hotspots with local Moran's I p-values of less than or equal to 0.05. And again, from an exploratory data analysis, this is very interesting, but let's see how we can actually convert it to predictive features for our model. What we're going to do is try to find areas that are not only significant at the 0.05 level, but are hyper significant. So here I'm looking at p-values. You can see a very small number, very hyper significant hotspots. And then what I'm going to do in this latter part here is measure the average nearest neighbor distance from every location in San Francisco to its one hyper significant fire hotspot. And we can then map the exposure, of course, from every location in San Francisco to its very significant hotspot. The black grid cells are those hyper significant hotspots. And there you go. We have a measure for every location as exposure to a fire hotspot. And this, of course, is a feature I just want to mention that we can use in our model. It is part of the final net. So it is, we now really have every variable we need to develop a simple fire risk prediction model. R is particularly slow as I'm trying to record this video on my laptop. So again, these are everything we had before: count fires, vacant nearest neighbor distance, year built, building square footage, graffiti, distance. We have a neighborhood for every grid cell. We know if a grid cell is a significant fire hotspot, and we know its distance to its nearest significant fire hotspot. And now we move into section 4 on modeling and validation. And in this section, we're going to introduce spatial cross-validation. But before we do that, I just want to run a very simple regression to show you the outcome. The dependent variable of our regression is the count of fires. When we use count outcomes, one kind of regression model is a Poisson regression. There are many others that are good for count data. There's a good debate to have if we're in which model to use, particularly if we're interested in interpreting the coefficients. We are not interested in interpreting the coefficients, which is to say, for this workshop, I'm not particularly interested in having a robust measure on the effect of, say, graffiti exposure to fire risk. And in fact, when you do this in the real world, you can use a random forest or a gradient boosting model. The more complicated machine learning models to try to predict count data. That works just fine. But I know some of you would like to see a regression table, so I can estimate one here. Again, we're regressing count fires on some of the variables, some of the features that we've created. You can see many of them are statistically significant, except for building square footage. Many of these could be collinear. We don't know the direction of causality, et cetera, et cetera. But again, I'm not really interested in these coefficients. I do want to let you know that they are not, that the regression model we're building is not spurious, that there is some predictive signal that relates these risk factors spatially to building fires. And in the real world, we want to take a lot more time in exploratory data analysis to try to understand the degree of collinearity, to try to understand the degree of correlation. Obviously, we want to create many more risk factors, and we want to boil these down to a system of risk factors that are statistically defensible. All right, now on to spatial cross-validation. So again, we're going to be interested in the latent risk of fires, which is to say that there is fire risk in locations for San Francisco, despite the fact that a fire hasn't actually occurred there before. And I mentioned to you at the onset that the most important consideration of this model is that it's generalizable, that it performs with equity across all the neighborhoods in San Francisco, regardless of factors like race and class, or even the fact that in the Tenderloin, say, there is a huge density of fires, a unique outlying density of fires. Imagine that one neighborhood has a really unique experience like the Tenderloin. When we do spatial cross-validation, we're actually going to ignore the Tenderloin experience by holding it out. What we're going to do is we're going to hold out one neighborhood. We're going to estimate a regression model on all of the other neighborhoods, and then we're going to predict for that holdout neighborhood. And every neighborhood will have the opportunity to serve as the holdout. And this makes sure that when we're predicting for any one given neighborhood, that the prediction in that neighborhood will be a function of the experience, the fire risk experience of all of the other neighborhoods, and not just the nuances of that one individual neighborhood. And we call this leave one group out spatial cross-validation, in that the group we're leaving out is a neighborhood. And again, the goal is to have some predictions that represent the collective experience citywide and not overly weighted or overfit by a single neighborhood experience. So we're actually going to run the cross-validation twice using two sets of variables. The first here, reg vars, includes the 4 of our exposure variables. The second one, reg ss vars, includes the spatial process variables. Fires is significant and fires is significant, the distance to the significant fire hotspots. And I want to run 2 regressions to show you the sort of value add when we model the underlying spatial process. I have included this function here that's less than reproducible that does the leave one group out spatial cross-validation. What it does is that for every neighborhood in this case, we're going to create a training set that is every neighborhood but one. That one will become the test set. Then we have this regression where we're regressing the count fires based on all of the variables that I mentioned up here. And we will issue predictions for all the grid cells in that neighborhood. And finally, bind together all the predictions for all the neighborhoods and return that in a simple feature format. So I'll read that function in. And I will run this cross-validation, spatial cross-validation twice, again for just the variables, just the risk factor variables, and then once again for the spatial process variables. And what you'll see when I run it is that it's going to cycle through all of the different neighborhoods citywide. It finished for the first one. It's now moving on to the second analysis. With each neighborhood that you see popping up, that neighborhood is acting as the holdout, as the test set. And that's now complete. Obviously, this process would go a lot slower if we were using a more complex machine learning algorithm. All right, the next thing I want to do is to look at model errors. And what we're going to do is we're going to subtract a prediction, a fire count prediction, from the observed count of fires. So this reg summary layer is pretty simple. Each row is, again, a grid cell. We know the count of fires for each one of these rows, and we have predictions. So, the count of fires, the observed count of fires is 0. We have a prediction that's very small. We can subtract the 2 to get the error. And we have 2 different kinds of regressions. Those are just risk factors. And then we have with the spatial process variables. This is in long form, so they're stacked on top of each other using rbind up here. So we have a measure of error for each grid cell for both regressions that we've created. We're going to calculate some goodness of fit measures. We're going to group by the regression and by the neighborhood. CVID is neighborhood in this case. We can calculate the mean error, where we subtract the count of fires from the prediction. We can calculate the mean absolute error, or the MAE, which is the mean error on an absolute basis. And we can also calculate the standard deviation, which is a measure we won't go into here. And then, not surprisingly, we can map these errors by neighborhood and by regression, which I think is a pretty revealing map. So again, I've sort of rolled up the grid cells to the neighborhood level. The map on the left uses just the risk factors, whereas the map on the right uses the spatial process variables like exposure to significant hotspots. When you look at this map, if you studied it for a moment, what you'd see on an absolute basis is that errors are higher, and in particular, they're higher in the tenderloin area, because without the spatial process variables, we're unable to predict that hotspot. Let me say it again. Without those spatial process variables, such as distance to significant fire hotspots, we're unable to predict these areas of highest fire risk, in this case, the tenderloin. When we include those features, that error comes down dramatically. So if you are an experienced predictive modeler, you will probably understand why including some features, the dependent variable, obviously helps the predictive power of our model. And the trick is not to overfit on that. We want our risk factors to play an important role. That's the underlying spatial system that we're trying to model. But we also want to try to understand some features of the dependent variable that will help us predict. And doing this well without overfitting is beyond this workshop, but it is certainly possible. If we think that we are overfitting based on these spatial process models, there are ways of toning that down, either through ensembles or otherwise. But the lesson I want you to take away is that we try to understand the underlying spatial process of our dependent variable. It makes for a more meaningful predictive model. So let's take a look at our predictions. We actually saw this map above. Of course, I've thrown an error someplace. And instead of going through and troubleshooting this, I showed you this map above. Let me return to it here. We have just created measures of risk predictions for every location in San Francisco. And what I really want to do, what I said to you, is to try to understand, if I was the San Francisco Fire Department and I was interested in creating a targeting tool for fire inspections, which buildings and which areas should I inspect first? Should I go by the kernel density or should I go by the risk predictions? I mentioned to you that the kernel density is useful, but it tries to understand risk really as a function of where fires have occurred in the past, whereas the risk predictions is able to account for these spatial risk factors, which may reveal latent risk, places at risk for fire, despite the fact that this rare event hasn't actually occurred yet. We should consider both the kernel density and the risk predictions as predictive surfaces. And I want to spend the final section of this workshop trying to understand those two predictive surfaces and compare them both to each other. I'm not entirely sure why this code block isn't working, but it generates that image I just showed you. And in the last section, it is very difficult to try to understand which is the best, the kernel density or the risk predictions. Typically, what I write in here is that you would go and study what a fire analyst does in San Francisco and ask them how they make decisions about where they inspect. And we're going to assume that the sort of business as usual approach for targeting these resources is the kernel density. And to make this more challenging, this is where those 2021 fires are going to be used. So we're going to have our predictions based on 2017 through 2020, and we're going to test those predictions on actual building fires from 2021. All right. Now what we're going to do is we're going to create two different risk surfaces, kernel density and risk prediction, and we're going to carve them up into 5 different risk categories. And in particular, we're going to be interested, these are just percentiles, but we're going to be interested in this 90th to 100th percentile. So we're going to create the kernel density as we did before. We will spatial join that kernel density to the final net, taking the mean density. We'll chop it up into 5 risk categories. And then we are going to spatial join to that the fires from 2021. And so we will know the risk based on the kernel density from 2017 to 2020. And then we will know the actual fire count from 2021. We'll do that for the kernel density. And we're going to do that again for the risk prediction model, and specifically the risk prediction model that includes the spatial process features. Same thing, split into 5 risk categories. We will append to those the count of fires from 2021. And let's map them so you can see what I'm talking about. All right, so we have, first of all, we have 2 risk surfaces, the kernel density and the risk predictions. They look different because we've chopped them up into 5 risk categories. The yellowish areas are those areas in the highest risk category, the 90th to 100th percentile. And I want you to kind of blur your eyes and try to understand how many of the 2021 fires actually fall into that highest risk category, which is to say, which model, which predictive surface, kernel density versus risk predictions, captures the most amount of actual fires from the following year. It's kind of hard to tell by looking at it, although you can see that when we're only focused on fires that have happened in the past from kernel density, we have this gigantic hotspot in the middle. Whereas the risk prediction model is more nuanced. You can see there are pockets of risk that show up throughout the city and not just in the Tenderloin neighborhood. Let's look at another way of trying to understand or compare these 2 predictive surfaces. by taking the rate of 2021 fires for each surface. And specifically, we're going to be interested in the highest risk category, the 90 to 100. And if we just look at these two bars right here, what we can see is that the risk prediction model picks up a higher rate of 2021 fires than the kernel density model, which is to say that the kernel density model is a less effective targeting tool relative to the risk prediction model. And again, it's because including our exposure variables highlights some of these areas outside of the main hotspot that have a higher latent risk for fires, which is to say, despite the fact that fires have not occurred there, there's still risk for fires. And that brings us to the end of the workshop. I hope you found this useful. This entire RMD, as I said, can be found on the GitHub repo that's in the comments of this video. And I urge you, please check out my new book, Public Policy Analytics, where you can see a more complicated version of this use case and many other machine learning, spatial and aspatial use cases. If you're interested in some more work, you can follow me in those places. If you are interested in a more formal graduate education about these methods, and particularly the application of these methods in government, then please check out the MUSA program, the Masters of Urban Spatial Analytics at the University of Pennsylvania. Thank you so much, and have a pleasant afternoon.